All right, y'all, round 5. Now, just because this is the last problem we're doing doesn't mean this is the only type of problems that you're going to see, right? We've had situations where we've drawn velocity graphs for multiple phases. Something starts at constant velocity, then it moves at a faster constant velocity. Something's moving at constant velocity, and then it speeds up, right? So you can have problems that are going to involve more than just, say, one straight line, right? So, but just because we don't cover that here doesn't mean you won't see that in class. But the basics are the same. What we're doing here, the basics, the fundamentals, are all the same, right? So you can even have something that looks like this, right, and goes like this, right? You should be able to break that up into different pieces and calculate what's going on in terms of displacement, etc., etc. Okay. So like I'm saying, disclaimer, these are not the only type of problems you're going to experience, right? You're going to experience problems that are similar, for sure. Problems that have the exact same graphs, but instead of a cheetah, it's an ostrich. I don't know. It could be a dolphin. It could be a car. Insert whatever your imagination wants to, right? But when we're going through this, these are what our graphs are going to look like. It's not just, it doesn't have to just be one line. That's all I'm trying to say. But all the fundamentals apply. Areas are always the same. Slopes are always the same, etc., etc. Okay, disclaimer over. A racer is running at velocity v1. Racer speeds up to v2 with a constant acceleration a. How much distance did the racer travel while speeding up? All right, here we go. Coordinate axis to the right, positive. I'll just say this right here again is x equals 0. It could be 100, but again, how much distance did I travel? All right, here we go. There's x1. Here is x2. All right, and I start at some sort of velocity, don't I? So now I start with some sort of velocity going to the right, v1. This is supposed to be x, not v. And then I speed up. Okay, so that means I'm going to have a bigger line going to the right now. v2. Great. Once again, I'm trying to solve for displacement, right? Displacement would be this right there from x1 to x2, right? That's my delta x, and that's what I'm trying to solve for. All right. Picture done. From the picture, I can come up with my graphs pretty straightforward. My initial velocity, I do have one, and it is positive right here, v1. v2, sometime later, I'm at a faster positive velocity right there. There we go. Ba-bum. v2. Right, my slope is positive, which means acceleration is positive. There you are. Okay, also could have gotten that, moving in the positive direction, speeding up, therefore acceleration is positive, because they have to be in the same direction. All right, I'll do this color. Haven't used this one yet. Now we're trying to, again, solve for displacement. Last time, we decided to start with velocity, because the velocity graph is where you solve for displacement. So from here, we can, well, we're going to have to break this up into a couple different groups. One's going to be this part right here. I'll call this delta x1. And then we'll have another one here that is delta x2. Maybe, oh. Right? So I have to break up that area into two different things. It's not very pretty there, but hopefully this will help. Delta x total is going to equal, I'll go into different colors, delta x1 plus delta x2. Okay, so how do I get that total? Well, delta x1, what is that? That to me is this piece right there. It is a rectangle. It's a rectangle whose base is the time and whose height is literally v1, right? So I end up with delta x total is equal to v1 times t plus x2. I'll change colors for this. x2, that was that top half of that integration. So we've done this before where we took and we had a piece of the graph we did as a rectangle, another one as a triangle. We're doing the same thing here just to make our calculations a little bit easier, right? So we have delta x2 is a triangle, 1/2 times the base. The base is still that length time t, and the height here is delta v. How much did you speed up? Delta v. Okay. So from here, let's see, trying to solve for x total. Do I know v1? Yep, running at v1. Runs up with constant acceleration. Oh man, I do not know time. Time comes up twice in this, but I do know how fast I speed up to. I do know a value I have. Okay, so there's a problem. I don't know time. I don't know the value of time. Well, where do I get that? You just don't toss your pen, right? Just, don't break your computer screen. Just be like, what do I do? I don't know what to do. Tell me. Tell me. I will. We're working through it, guys. Right? Here we go. We have another graph to use. Right? So delta v is that area under this graph. It's equal to acceleration times time. So if I solve for time, time is equal to delta v over acceleration. Where do I know my delta v? I do, and I know the value of acceleration. So what you get to do here is what we call substitution. 2 equations, 2 unknowns. Let's do that one. All right, so I take this delta v and over a, and wherever I see t, that's what I put. So I put delta v over a for both of those right there. So I'll make this delta x total is equal to, I'll go back to original here, v1 times delta v all over a plus, I guess maybe I should have made that brown because I made that substitution there, but then we have 1/2 times t delta v over a times delta v. All right. Wow. Okay. So it's not difficult going on here. It's a little substitution. So maybe that is difficult. I shouldn't say that, right? But you probably look at this and just see a bunch of letters, right? But remember, those letters have meaning, right? I won't run through a demo on this one just for sake of time. I think I've done enough demos, made you guys suffer through that. But you should be able to run through this with the same problems, with numbers. Give it a try, and hopefully you'll end up right where you need to be. All right, everybody, all done with this one. Time to have a good night, have a good morning, whenever you're done. Anyway, good job. I'll see you in the next video.